Well, hello, everyone. Here we are at Lecture 1D, talking about gas mixtures. So when we have mixtures of gases that are in a vessel, for example, just if you have a sample of air that's going to have several different gases in it, the pressure exerted by each of the gases present is completely independent of the other gases that are also present. So in other words, the amount of pressure uh, exerted by a particular gas is proportional to the fractional amount of each gas. And the amount of pressure that is exerted by each gas is what we say is its partial pressure. Now, Dalton's laws of partial pressure say that the sum of partial pressures of all the gases present in a sample have to add up to the total pressure. Hopefully that makes sense. So P total has to equal the pressure of component A plus the pressure of component B plus the pressure of component C, etc. And it turns out we can apply the ideal gas law to the partial pressure of each gas. And so we can say the partial pressure of A times the total volume, because A will still fill the entire volume, that's going to equal to the number of moles of A times R, which is a constant, and T, which is always going to be the same for all the gas samples within a particular vessel. So what that equation shows us is that the pressure of gas A becomes directly proportional to the number of moles of gas of A, or B, or whichever gas you have to be looking at. But we can express that in terms of something that's called mole fraction. And all mole fraction is basically what fraction of the total moles is the component that you're looking at. And so we can look at mole fractions of the different components, either looking at the pressures or by looking at the number of moles. And so we can say that the mole fraction of gas A, component A, would be equal to the partial pressure of A over the total pressure. That would also be equal to the same value for the number of moles of A over the total number of moles of all the gases. All of that would be equal to the mole fraction. We can express that another way, which would say that the partial pressure of A would be equal to the mole fraction of A times P. Now keep in mind for mole fraction, if we look at that, the fraction given, it's Na over N, it has to be a value that's 1 or less. If you have a sample that's purely A, then your mole fraction would be 1. If you have a sample where half of the moles are A and half of the moles are other things, then it would have a mole fraction of 0.5. So your mole fraction value is always going to be between 0 and 1. Now we talk about that because many times when we're collecting gases over water, or maybe more specifically, over a solution where we have a reaction taking place and the reaction is evolving a gas, we're collecting that gas. And we might be measuring the amount of that gas by how much pressure is exerted by that gas in the vessel. We have to remember a thing called vapor pressure. Humidity in our air arises from a property called vapor pressure. Obviously, as we walk around in our everyday lives, the temperature is not 100 degrees Celsius. So how do we have any water in a gas phase at 25 Celsius or 20 Celsius? And this is due to something called vapor pressure. So even though we are below the boiling point of water as we walk around our everyday lives outside, there are water molecules that have enough energy to turn into a gas. And we'll look in that more detail in a little bit later talk in this particular lecture. When we measure the pressure of a gas taken over water, we have to account for any evaporated water vapor as well, because evaporated water vapor is water gas, and because it is a gas, it will exert some pressure. So this is highly dependent on temperature, but it's also very easy to tabulate, as we've done here. So this is vapor pressure of water versus temperature. Now you'll notice here that the pressure is measured in millimeters of mercury, and this is just so that we have a reasonable number to work with, as opposed to tiny fractions of bars. So we see that as temperature goes up, the vapor pressure of water increases. And we see that when we get to 100 degrees Celsius, we actually reach 1 atmosphere of pressure at 760 millimeters of mercury, which is 1 atmosphere. And that is the boiling point. And so that's where the vapor pressure of water is equal to the pressure of the atmosphere, and water can freely turn into a gas. Basically, all of the molecules inside that liquid water have enough energy to turn into a gas when it's at that temperature. And so it would actually contribute an atmosphere's worth of pressure at that temperature. When you're at a lower pressure or lower temperature, you can see that water does exert some pressure because some water vapor does escape the liquid, but it contributes significantly less than what it does at 100. But notice that even at 0 degrees Celsius, so that water, if it's water liquid at 0 Celsius, it's in equilibrium with solid ice. It still has a vapor pressure. There are still a small number of molecules of water that have enough energy, thermal energy, in order to escape from the surface of the water and turn into a gas. So even at 0 degrees Celsius, we still have to account for 4.58 millimeters of mercury worth of pressure just from the water. So here's an example of when you might be taking a sample of gas that's over water. If you have zinc put into hydrochloric acid, it's going to evolve hydrogen gas. In order to collect that gas, you generally would run it through tube and then run it into a beaker that is filled completely with water before collecting the gas. And then as the gas builds up, it displaces the water, and the water prevents the gas from escaping out the bottom. But if this is done at room temperature, you're going to have about 23, 24 millimeters of mercury of pressure that is not due to hydrogen gas, but due to water vapor. So if you're trying to measure how many moles of hydrogen you've collected based on pressure, you have to subtract out the vapor pressure due to water in order to make that calculation.